Audio check. That's what I'm gonna do.
Yeah, especially because oh, that's true.
Right now, it's really close, only the red. But also, the top of the cap here is also the big
The participants are able to help themselves. You're still here. Yes, that's why you can. But yes. Probably not
I guess.
All right, everyone, thank you all for coming to the first of 8 Hot Science Colloquium sessions. The Hot Science Summer Series is a collection of talks from STScI and JHU affiliates on 8 broad topics. Today, we're going to be discussing stellar populations. We have 2 speakers. First, we have Dr. Peter Zeidler, and as the second talk, we're going to hear from Dr. Adarsh Ranjan. So thank you very much, and give our speakers a great round of applause.
Thank you. So we know that typically stars form in clusters or clustered environments, and these young star clusters, typically 5 million years, 10 million years old, harbor most of the massive stars in the universe. They also have like a rich pre-main sequence population that still have protoplanetary disks in and around these O and B stars, and they show active and ongoing star formation in the surrounding gas and dust ridges, so in the H2 region, where you can also then find those deeply embedded young stellar objects. While the massive stars dominate the region's flux budget, they are only few in numbers, but they have a huge impact. So their pre-supernova feedback processes can expose the young star clusters, so they blow away the gas and the dust. They erode the surrounding molecular clouds, creating those beautiful pillars. They create photodissociated regions, and they irradiate protoplanetary disks, which also then can lead to early disk truncation or even dispersal. So they have a huge impact on their surrounding environment. And it's believed that in some cases, they may even drive star formation into the surrounding gas and dust shells. So like the newly formed stars there may be triggered by those massive stars. On the other hand, the low mass stars and brown dwarfs are a lot in numbers and therefore also dominate the region's mass budget, which means they're responsible for the gravitational potential, so also have a huge impact on the survivability of a star cluster. They harbor also most of the protoplanetary disks, And some, like here with the marked in the yellow diamonds, this is NGC 346 in the SMC. So some are still deeply embedded in the surrounding gas and dust shell, so they are very young, which means these star clusters are the perfect location to study star and planet formation and the evolution under the influence of external far UV radiation, and also the interactions between those massive stars and their surrounding gas and dust. In order to study those young star clusters in full, we need to observe them at a broad wavelength range, ranging from the optical and UV, from the massive stars to the near and mid-infrared for the most embedded objects in the surrounding clouds. And we are doing this mainly with 3 telescopes and multiple instruments: Hubble, VLT MUSE, and JWST. With Hubble photometry in the optical, we can typically get like basic cluster parameters such as age, distance, their total mass, the reddening via like isochrone fitting to the color magnitude diagrams. Additionally, we can also get beautiful extinction maps, like pixel-to-pixel extinction maps, where we then can correct each individual star for its reddening. And with multi-epoch HST and now also JWST observations, we get stellar proper motions. Like here, again, for NGC 346, where we discovered that it has this nice spiraling inward motion of their stars. We can do similar things with VLT MUSE. VLT MUSE is a large field of view IFU with a field of view of about 1 square arc minute. So it's big enough that we can actually properly map Milky Way star clusters, almost similar to photometry. Since it's an IFU, we get spectra at each point, which means we can measure stellar radial velocities with an accuracy similar to what we've done with the Hubble proper motions, which means we can actually truly get the 3D kinematics within such a cluster, including we can also get the line of sight kinematics of the gas at each point. So we can truly study the interactions between the stars and the gas. And this is even possible at SMC distances. We're here, again, for NGC 346. This is the central square arc minute, so this is only 1 MUSE pointing. We managed to extract around 450 stellar spectra, and 52 of which we were able to measure radial velocities, showing that the core is actually rotating. So the rotation axis goes like this. And the core is actually rotating with a similar velocity as we see in the spiraling inward motion through the proper motions. So it's truly complementary. If we want to study, though, the massive stars in detail, we need to go to the infrared and to the UV and the far infrared, far UV, where basically their SED peaks. And with this, and especially with this spectra, we can directly access the far UV fluxes through the continuum and the stellar winds through certain lines. So we can directly determine how these stars may impact the surrounding gas and dust by then combining these with the optical and the near-infrared data we get through the other telescopes. So we can also see how these stars, in relation to their far UV radiation, may actually drive star formation into the surrounding clouds. And last but not least, JWST. In the near-infrared, we need to observe near and mid-infrared to get the deeply embedded premium sequence stars and young stellar objects in the clouds. And with JWST near and mid-infrared and spectroscopy, we can actually get or identify premium sequence stars through color magnitude cuts, and also detect and classify their protoplanetary disks. We can measure directly through spectra the mass accretion rates onto the host stars, and also determine not just the mass function in general, but especially the low mass and substellar initial mass function. I come to this a little later in the talk in more detail. So overall, by combining all those instruments together, we can get the full 3D picture of a young star cluster. And not only can we observe it from the UV to the mid-infrared, so from the exposed population to the deeply embedded one, but this is also a progression in age. While those stars basically in a region tend to be the oldest with a few million years, the newly forming stars and YSOs in the gas and dust can be as young as 100 million years. So overall, our goals are to study how environmental conditions impact cluster formation and evolution, how the initial mass function, the core evidence on how the universe turns gas into stars, works, and if it's universal, so if this mass function is the same everywhere. And also how these conditions may impact the formation and evolution of low mass stars and especially brown dwarfs. Since I will focus more on brown dwarfs for the rest of the talk, let's see, what are brown dwarfs? So brown dwarfs are substellar objects that are more massive than gas giants, but less massive than main sequence stars, which brings them typically in a mass range from 13 to 75 Jupiter masses. They majority form independently like stars, so they are through the collapse of the giant molecular clouds, yet they never reach a mass where they can sustain hydrogen fusion. That also means they are on a continuous cooling sequence due to the lack of fusion. So basically for a constant mass, they get dimmer with age. They preserve lithium, which is especially important for older brown dwarfs and a clear criterion if an object is a brown dwarf or rather a low mass star. And many also actually can have clouds in their atmospheres. But they have one thing in common, they are very faint. And here on the right, you see a Hertzsprung-Russell diagram where you have the most massive O stars here on the top left and the brown dwarfs on the bottom right. So, and since in those young star clusters we have both brown dwarfs and those O stars, but we want to detect brown dwarfs, we actually need to detect objects that are 20 to 25 magnitudes fainter than their direct immediate neighbors in the same region. So before JWST, this was basically impossible to do outside the Milky Way for young objects in like those star-forming regions. And why is this important? Since, well, we can detect and find brown dwarfs in the solar neighborhood. This is true, but the solar neighborhood limits us in the parameter space. Since the solar neighborhood by definition has solar conditions, which means we can, in the Milky Way, we basically can only find young brown dwarfs at solar or supersolar metallicity, but we cannot find any young brown dwarfs that are at subsolar metallicity, at least not in a statistically significant number. To do this, we actually need to go outside the Milky Way and into other galaxies. Now you may ask, why is this important? Well, we know from stellar evolution that metallicity actually can have a huge impact on the evolution of stars and their protoplanetary disks. To a certain extent, also on the potentially also on the brown dwarf population. Like for stars, for example, we know that stars at lower metallicity burn hotter, therefore they have higher fire-UV fluxes, they have lower stellar winds and lower mass loss rates. So metallicity basically has an impact on how they may interact and how they impact the surrounding material. On the other hand, protoplanetary disks with a lower dust content are believed to have less shielding from UV radiation, so they may truncate more, and they may have a shortened disk lifetime, which can hinder planet formation. For brown dwarfs, from like theoretical works, we think that the hydrogen burning limit, the mass basically at which is necessary to start fusion, increases with decreasing metallicity. So you need an object to be more massive to actually become a star at lower metallicities, which again can have an impact on planet formation zone because those stars then don't radiate, or those objects don't radiate. It also has an impact then on, or may have an impact on the initial mass function. So as I mentioned before, this is the statistical function here, Chabrier-Kruper, how stars in a certain region are distributed. And basically, it's believed that this may be actually universal. So the question is, though, is this the same distribution everywhere? And it's basically the number of stars per stellar mass spin. And observing in the solar neighborhood, it seems to, most observations of young star clusters point towards its universality, so that it's actually, it more or less statistically has this shape. But recently with JWST, there has been found that there is a decrease in brown dwarf to star ratio with stellar density, or that also the peak of this may shift with metallicity. And since the low mass regime dominates a star-forming region's total mass, slight changes in this can have a huge impact like on the gravitational potential and survivability of those clusters. So the question is the mass function truly universal? And to answer this, we need to observe many star-forming regions in a more statistical manner across many different environments, especially low metallicity. And the best thing to do is this in the Magellanic Clouds, because the Magellanic Clouds have either half solar metallicity for the LMC or 20% solar for the SMC, yet they are near enough that we still can resolve their full stellar population in great detail, even in the densest regions, especially thanks to JWST, where we can even go down to the hydrogen burning limit and below, as we will see. Furthermore, the SMC also has the conditions that is more similar to like the time, the so-called cosmic noon, the time when the universe peaked in star formation. And this is exactly what we are currently doing for a young star cluster called NGC 602. It's located in the SMC, or better in the wing of the SMC, so a little bit in the outskirts towards the LMC. And it's a star cluster in isolation, so there are not that many effects from the outside. It's a star cluster that's roughly 2 million years old and has the mass of Orion, yet it formed significantly more O and B stars, more similar to like Trampler 14 in the Milky Way. From like HST observations, we also know that there is a very prominent Freeman sequence, and Spitzer also revealed that star formation actually may be driven into the surrounding clouds. So Spitzer detected some deeply embedded YSOs that seem to get younger the further you go away from the cluster. The most massive member of that cluster is an O3 star with about 43, 45 solar masses, and which is responsible for the vast majority of the far UV flux in that star-forming region. And we observed this cluster in cycle 1 with JWST, NIRCam, and MIRI. This is how it looks like. So this is the cluster, this is this O star I was talking, and Spitzer found a lot of like YSOs in those pillars. Now with JWST, we already saw that many of those objects are actually multiple ones, because Spitzer simply lacked sensitivity and resolution at that distance. Distance is about 61 kiloparsec. So I will focus mainly on the NIRCam observation for the rest of the talk, and we observed it in total with 8 filters detecting around 16,000 point sources, which of course include SMC field stars and also many, many, many galaxies in the surrounding that are true point sources. So to further analyze that region, we divided it up in a cluster region and a background field outside. So there, it's basically no cluster stars anymore there. So this is truly SMC field or background galaxies. And if you now plot color magnitude diagrams, I from now on only show one specific one. We used many filter combinations to actually create those cuts. But what you can see, the control field and the cluster region are significantly different to what they show. While both show the old SMC field, only the cluster shows the Freeman sequence stars as we expect. Also, only that has the main sequence and embedded YSOs, while both fields show where galaxies are located. So you see there are plenty of galaxies in the background. Those are only the point sources, because we made cuts, so extended sources are not even in there. If we now focus on the cluster population itself, we see this is here, this is a 2 million year isochrone, stellar isochrone. And stellar isochrones, this one ends at around 0.08 solar masses, which is roughly the hydrogen burning limit. Now you see that there is an extended population that is redder and fainter than the faintest theoretical star on that isochrone. So we were wondering, what are those objects? And we looked into different, like we basically looked if any other object in that region can mimic stars there. So one is like, we checked, can these be SMC field stars or Freeman sequence stars that end up here due to extinction? And even though, yes, this is the reddening vector in this one, it would be possible, but if you combine multiple filters and multiple color magnitude diagrams, it's truly not possible. And they also, so they cannot be explained by reddening, and they're also not background galaxies. So the one thing we said that is left are that these objects should be or must be brown dwarfs, because brown dwarfs are fainter and redder than stars. And indeed, if we now overplot brown dwarf isochrones, they actually match this population. And by fitting, or by using now cuts in multiple color magnitude diagrams, we actually could select 64 objects that are in agreement with brown dwarf isochrones and evolutionary models, having a mass range between 50 and 84 Jupiter masses. You see here, the mass is here slightly higher than the 75 I stated before, and this is why 84 Jupiter masses is about the hydrogen burning limit at SMC metallicity. This also makes these the first ever detected young low metallicity brown dwarfs outside the Milky Way. And furthermore, if you still think, well, there might be background galaxies or so, this is their distribution. So in red, we see the Freeman sequence stars, which we know they are cluster members. And in yellow, we see our brown dwarf candidates, which statistically follow one-to-one the pre-main sequence population, which also then led to the conclusion that since they're spatially co-located, that these truly formed co-evenly with those stars, which means they are a true continuation of the stellar mass function into the substellar regime. So now with this, for the first time, we actually can observe this parameter space. We actually, for the first time, have young brown dwarfs at subsolar metallicity, which also means with this, we can actually adjust current models and brown dwarf models, because now we finally actually have observations. So for the first time, we can also observe in a low metallicity environment objects from its most massive member, like an O3 star, down to like 50 Jupiter masses. But you were wondering, I was talking so much about the IMF. Have we actually determined it? I need to disappoint you, we haven't yet, because these observations were actually never intended to detect brown dwarfs, so they are relatively shallow for JWST standards. But we asked for cycle 4 NIRSpec and NIRCam data, and we got granted 77 hours of photometry and spectroscopy. So with NIRSpec MUSE, we will target around 45 of those brown dwarf candidates to actually get spectra, to get their age and metallicity dependent features. But in addition, we also get another 6 NIRCam filters with which we plan to go as deep as 15 Jupiter masses. So these will be actually deep enough to truly get the IMF in that region. So for the first time, we will be able to study the full IMF in that region. What else next? So we also have, as I said, MIRI imaging. This is a MIRI image. It's not as pretty as the other one. The difference is I made this. The other one, public outreach made. And currently, Bina is working with the MIRI data to characterize those deeply embedded YSOs in the gas and dust ridges. So seeing whether there is still significant ongoing star formation. And then in combination with STS observations, we can see if the stars may be actually responsible for driving it into the clouds. In this process, she also found a deeply embedded protocluster object that is here. You can't see it behind the star because it's actually not visible in the near infrared at all, but you can see it here clearly in the MIRI data. And very, very preliminary estimates as is like this should have like a total stellar mass of around 700 solar masses. Because you can, I mean, if you would go into more detail, you can also see multiple peaks and which you can do SED fitting on. We also have, I mean, this is the Hubble image of the region, but we also have already MUSE data at hand, where Jimena will work on or start working on in September. And with that MUSE data, she will extract individual stellar spectra with which we then can measure stellar radial velocities and determine that to an accuracy of around 2 to 3 kilometers per second to get the internal kinematics of the stars and the gas. And also we have an intern that is coming in June from the University of Arizona, who will actually work with Linda Smith and myself unlike the 11 STS spectra we have of the 11 most massive stars in the region. So with these, we can, as I mentioned in the beginning, directly measure the far UV fluxes. And together with all the other data, we will be able to see how those stars actually impact star formation and how efficient, as I mentioned, it drives it into the surrounding gas and dust. That's it from my side. Thank you.
Wonderful talk. Do you have any questions online or in the audience? Zia?
Yeah, super cool data, Peter, and great talk. So one question in star formation, right, is how much, as you kind of, I think you said in the last slide, do the massive stars and their activity influence the formation of lower mass stars, right? And so throughout your talk, when you were focusing on brown dwarfs, I was curious, well, you have very massive stars there, which you targeted with FEV, STS. Do you see any, in the distribution of the brown dwarfs, like any maybe like lower density of brown dwarfs closer to the massive stars?
So we don't see anything, but this doesn't mean it's not there. The thing is, with the brown dwarfs, we're really at the detection limit of what we can do with that data set. So we see a lower density in the center, but this is mostly to incompleteness rather than saying, oh, there are less brown dwarfs. But since we are at the detection limit, there is basically, with this data set, almost no point of running completeness tests, because the correction will be so uncertain that you cannot make any good predictions. With the new data we will get, we should actually be able to answer this if there is any difference. That's one of the goals.
Any other questions?
So it's a different topic. So you, in the beginning, you mentioned about the lithium abundance. Would be one test for, if you detect, that would be a brown dwarf. I suppose you cannot detect any, it's too faint to get any lithium observations. Is that right?
So theoretically, NIRCam prism goes blue enough that you could actually see a lithium line. The problem is that it takes about 100 million years for stars to burn off lithium at all. So at that age, around 2-3 million years, both brown dwarfs and stars still have lithium. So that line can't be really used to distinguish at that age. Sadly, that's a problem, but yeah.
So what I want to say, regardless, just if you detect lithium, the lithium abundance, if you can actually detect and get the abundance, that would be a fantastic result.
Yeah.
Lithium abundance, so far in the galaxy, there has never been something which is closer to primordial. This would be low metallicity stars, which would give you in the galaxy, only the halo stars are the only ones for measure. Here, it would be a low metallicity star, whether the lithium abundance is close to primordial or not.
Yeah, the problem there is that, so the spectra we will get will be NIRCam prism, which is has a resolving power of like 40 at that wavelength range, because any other higher resolution like the M gratings or H gratings, like no chance at that distance. It's like simply you need a bigger mirror. It's like, even with prism, it's borderline, but we tried, because yes, it would be great to have a little higher resolution, but there was like no way.
In the back there first.
Are there any hints of the brown dwarfs in the 346 data, or is it just too complicated and not deep enough? Or
we have not looked yet, but yeah, it's the thing is also that cluster has one advantage: it has relatively low density, relatively low stellar density compared to many other SMC or LMC clusters like NGC 346, where there is similar data set. It's a GTO program, but the stellar density is so much higher. So even though the data is a little bit deeper than this one, in the cluster itself, we are mostly confusion limited, not depth limited anymore. But we will look, especially in the outskirts, we may have a chance. But in the center, it's borderline. It's simply a confusion problem.
mentioned earlier on that the cluster was rotating.
The other one, not this one. Yeah, I mean this one we don't know. Let's put it this way. Probably it may, but we will see with the MUSE data Jimena will work on. We probably can see if it's rotating, because this one, I mean, it's a very nicely spherical cluster. So, yeah.
Yeah, thank you, Peter. 77 hours of JW is a lot of hours, right? How many of those will go to NIRCam? Or the 77 are to NIRCam only?
No, it's the 77 hours are both NIRSpec and NIRCam. So it will be per filter, per NIRCam filter, about 10 hours of exposure time. Okay. And about 8 hours for NIRSpec, if I have the numbers correctly in my head.
10 hours per filter is quite nice.
Yeah.
Do you plan to do anything with those background galaxies?
Me personally, besides trying to sorting them out. No, not much. No, like, I mean, I personally don't plan it. No.
All the people with interest.
Yes. No, I imagine. And please, I mean, of course.
Go.
I was just curious what the extinction was to those background galaxies, because I'm surprised we can see them. I would figure that they're behind a bank of dust, but that's not the case.
So the extinction towards the cluster in general is low. So like the AV to that cluster is 0.25 magnitudes.
I'm thinking of the extinction of the dust that's not in the line of sight to the cluster, that the cluster is clearing out.
Yeah.
That's what I was curious about. It doesn't look like there's that much dust once you get far enough away, which is interesting.
No, there is, but it's also like, as I mentioned before, it's like not directly in the SMC, it's a little bit outside. So it's like, that helps. That helps a lot. You can see that it's, where did it go?
I mean, normally when you see a blister like this cluster is making, you don't see anything behind the dust that the blister is in, but in this case you do.
Yeah. And you even see that the cluster region and the control field have, I mean, there's basically not like that the control field has like visibly significantly more galaxies or so next to it. So yeah, we mostly can see through.
Yeah.
Yeah.
I have one final question. So given that stars are going through like the CNF cycle and producing metals, for brown dwarfs, would their intrinsic metallicity be more closely matched to like the initial gas cloud that it formed out of, or is there other chemical evolution going on in brown dwarf?
I honestly don't know. Elena, do you know?
I'm guessing we would probably find different populations as well as weird stars with different ages as they were formed together, right? So, but it's something we'll have to look at. Although I don't know if we can be sensitive to, small changes in metallicity from, I don't know, 2 million years to 0.4 million years. That's a little, but yeah, it's something to look at for sure.
All right. Well, with that, let's give Peter another round of applause. So our next speaker again is Dr. Adarsh Ranjat. So let's give him a quick round of applause while he. The floor is yours.
Thank you. Hi everyone, thank you all for coming, and thank you to the organizers for organizing this amazing HotSci series. Before starting, I also want to thank my team members here at Space Telescope for the amazing work that they have helped me with. I'm going to talk today about the co-spatial study of neutral and ionized gas in the Grand Design Spiral galaxy M83. Should give me a minute. Let me keep it here. Okay. So let me start this talk with an overall story that is familiar to people, which is with the galactic fountain model. I guess you guys have seen it a couple of times. So really quickly, what this model says is how galaxies evolve in chemicals is how the intergalactic medium gas seeps into the galaxy through the circumgalactic medium. And when it reaches the interstellar medium, it kind of like, forms these little cloudlets of interstellar medium in which stars form. And once stars form within their lifetimes, stars will enrich the molecular clouds and further going out the regions outside, which is the interstellar medium. And in like general sequence, whilst the galaxy evolves within a couple of billion years, you would see also the enrichment of the whole galaxy itself. Now, with the enrichment of the galaxy, again, going back to this global model, once you have feedback from active galactic nucleus or stars like supernova or something, you would expel this gas back into the surrounding of the galaxy, which also enriches the galactic surroundings and leads to the chemical evolution, basically, of the universe. Now, we will focus more now on what happens inside these. So within these individual interstellar medium, star clusters form, a couple of them, or one, and then they would ionize the regions immediately around themselves, which is also, we can call them the H2 regions because the hydrogen is ionized. And surrounding this, of course, is the envelope, the bigger envelope of neutral clouds, which is H1 clouds. Now, so moving through this, why is this important? So it's important because different stars within these star clusters will be responsible for different kinds of elements being produced, and not just produced, but also being transported. So within, let's say, the outflows, within their function of outflows of different stars, or with different stellar types, or with different stellar ages, you will see different metals spreading out in a different way. And this is very nicely actually also described by Kobayashi 2020, where we see that, apart from the hydrogen, helium, and lithium, most of these elements that are formed within stars, and you can see that the contributions vary significantly, even amongst elements that are close to each other, like carbon and nitrogen. So moving on. So the quick questions that we want to answer is how, and this is the more important part, is how within these star clusters, different stars would impact the whole process of metal enrichment, not just within their immediate surrounding, but also within the local ISM. How can we do this? We can do this with multiple instruments. So we use Hubble data for UV, and UV spectroscopy will give us absorption by neutral gas and also by stars. And we also use data from LVT and VLT, which is on the ground, and these optical data will tell us more about the emission from the nebular gas. Okay. And here's an example, quick example. So as you can see from Hubble, we can get the UV absorption of neutral gas. There is hydrogen at 1215. This is sulfur, ionized sulfur at 1253. And you see the clear absorption feature, which can be fitted to get the abundances. And on the opposite end, we can see that the optical spectra gives us basically sulfur again, with the doublet, famous optical doublet, and H alpha plus N2 doublet. On top of this, if we look at this UV spectra, we can also get information about what kind of stars it is, how strong the outflow from the stars are, and what kind of stars are there, and their ages. So it's kind of like building a complete picture with these, multi-wavelength observations, and that's basically what we're trying to do. Now we have the target M83, the plot is chosen. We have the data, the stage is set. So, but what do we already know? M83 has been researched till death. So there's a lot of things that we already know about M83. So young star clusters in M83 have been studied a lot, but I'll focus primarily on the famous papers that did a co-spatial study, which is Hernandez 21, about neutral and ionized gas. And they focused on sulfur, and they said that one of their key measurements was that there's less amount of hydrogen than sulfur within the galactic center. If you see this plot of column density of X being the element, versus the galactocentric radius, which is R over R25, we'll see that the difference between sulfur here and hydrogen being much higher than sulfur in log scale, so that would be like 2 orders of magnitude. Now, the other important result from their paper was that the neutral, ionized, and stellar metallicities, with their measurements, agree with each other within the measurements. Okay, so what we know from literature is that M83 evolves through inside-out growth, like other disk galaxies. That's what it shows here, with the metallicity being a little bit dropping as a function of radius. And the strong line metallicity studies must account for multi-phase dynamics. It's important. And again, the third one is what I just mentioned, where there's less hydrogen in the center. So what our project aims is to build a bigger picture with adding in elements, so that we can get a more complicated or complex picture of the timescales within which the stars impact the interstellar radium. So how do we do this? So the current work is understanding the evolution of metals within the phases within these star clusters. And this is the M83, and I plot here the pointings of individual star clusters as color coded by their stellar age. And my aim eventually will be to compare different elemental abundances between phases, H1 and H2, which is ionized and neutral. And I'll do this as a function of both stellar age and as a function of the galactocentric radius, which is basically the distance from the center of the galaxy. Now, how do I do this methodology? So for neutral gas, as I showed this before, we can look at the absorption line in the UV spectra. We can measure a multi-component point profile, we can fit it, and then from these fit, we can get the total abundances. But these abundances are specific to the ions. So from these ionic abundances to go to total elemental abundances, we use photoionization models and correct for the ionization. In ionized gas, we fit the multi-component Gaussian in the lines. And the lines that we identify are like strong emission lines, forbidden, and auroral lines. And then from auroral lines, we plan to get the electron temperature, which we will use to calculate the abundances and correct for ionization again with prescriptions from literature. So let's focus on ionized gas first. So how we do ionized gas, or how it's done in the field, is we either look at strong line method, which is identifying the strong emission lines and then using different calibrators to obtain metallicity. Now, the problem with this is we get metallicity, but we can't get any abundances apart from oxygen. So other more precise method is to actually look at the direct abundance method, where we look at hydrogen and other lines, we get the density from sulfur 2 doublet, and then obtain the electron temperature from the auroral lines. And once we have the electron temperature, we can then further calculate the elemental abundances of each element. Now, the problem with this is that auroral lines are too weak in metal-rich or low-temperature gas. Basically, there's a correlation between how high or how strong your auroral line is and your temperature. Okay, so to resolve this, because we have very metal-rich galaxy, so to resolve this, what we do is we apply for a prescription that works or try to work. So for that, we first calculate the strong line metallicity, and we plotted different strong line metallicities as a function of each other to see what gives us a precise or a more precise one-to-one correlation. So here I plot R23, which is one of the diagnostics of strong lines, with O3 and 2 and other prescriptions by Dopita. And this is the one-to-one line, which is the dashed line going slant. And we see that the three calibrations are correlated. And the other important fact is that we see that the metallicity in M83 is significantly higher than even other star-forming galaxies. So further, we see that as a function of galactocentric radius, or R25, the O3 intro is the most reliable calibrator within the strong lines for at least our case, or our galaxy, for the clusters within our galaxy. And that's what we see here. There's less spread and more uniform distribution, and the trend is quite robust. So we use the O3 and 2 to further further see if we can get the electron temperatures or have a relation with the electron temperatures with the strong line so that we can calculate direct abundances. So here here I plot the 3 detected auroral lines and derived temperature from those auroral lines as a function of my O3N2 metallicity calibrator. Now, because we didn't detect it in all of our clusters, we have to rely on the fact that how robust our measurements are based on this based on this trend that we see when we plot our points with the points from literature for our galaxy M83. So then we see that the trend is most reliable for this specific point that we get from LBT. So we have one confirmation that this could be used as an average temperature, but it's not really, because if we wanna look at it in a straightforward way, every single cluster will have its own individual temperatures. So it's hard to basically rely on just one method or one confirmation. So what we do is we took all the 3 temperatures from all these 3 clusters, and we estimated the metallicity for our entire clusters to see whether they match exactly 1-to-1 with O3N2 method. And this is what I plot here. So in the gray points, you see one of the, so I take the temperature from object 1, which is one of the clusters, and I plot the points here. And this is the O3 metallicity calibrator in the y-axis as a function of direct metallicity derived from these temperatures. And again, the green and the blue consecutively are from other clusters. And we see that within the range that O3N2 is valid, as we know from QLE 2019, we see that the green points are the ones which are most consistent with the strong line methods. So moving forward, what we will do is we will say, okay, because our metallicity sort of matches best if we take the temperature from the LBT cluster, which is this M83F1_2, and we will use the temperature from these to get the elemental abundances in the ionized gas. So that's ionized gas. Now let's move to what we did for neutral gas. So for neutral gas, we got the total column densities from the multi-component void profile fitting of individual UV absorption lines for each element. And then it's more straightforward because then we apply photoionization models and then we get from ionic to elemental abundances. Now what they give us is, so these are different elements, and I've sort of given the primary mode in which each of these elements can be injected into the cloud through stars. So for example, iron will be injected from a type 1a supernova within a giga-year scale, as opposed to, let's say, nitrogen, which can be injected with AGV stars on 100 million timescales, as opposed to oxygen, which is much lesser, 5 to 10 million timescales by type 2a supernova. Now, I wanna put out a word of caution here that these are not the only methods that can inject these elements. These are just the primary methods that they do. So okay, so now we have elemental abundances for both neutral and ionized gas. Now we can compare them to infer different characteristics about the cloud and the environment. So what we do is we compare the abundances amongst phases. So basically on the Y, in the next plot, I'll put ionized elemental abundances, and on the X, I'll put the neutral gas elemental abundances. And we'll see as a function of these how they vary, and we can assume certain conclusions drawn based on that. So here it is. So you have the neutral versus ionized abundances of each element in different stamps here, and then color coded with different colors so that it's more clear to you. And what I've done is, so basically, the few conclusions that we can immediately draw with this is oxygen is more abundant in the neutral gas for at least more than 50% of the cases. Iron is significantly less in the ionized gas here. And so what we can infer is that it hasn't been long enough within the star clusters to see the next injection of iron into the ionized gas. Hence, the neutral gas abundances are higher. And the other thing is we can see is that the sulfur has a split split pattern, and it makes sense because sulfur, as you can see here, is both, like, it can be injected from type 1a supernova and also from core collapse supernova. So type 1a and type 2a both can inject sulfur into the medium, so makes sense. Yeah, so going forward, what we do is, because we want to know if there's any pattern as a function of stellar age, and that's what I plot here. So here the x-axis is stellar age of each cluster, as opposed to compared to the individual elemental abundances. So that's oxygen here for log O plus H, and this is nitrogen, and this is nitrogen enrichment, which is nitrogen over oxygen, and then iron. And immediately we can see that neutral gas oxygen shows a steady increase here, and nitrogen, however, in both phases is kind of constant. And neutral gas iron increases slightly, but stays constant in the ionized gas. So the blue here is the neutral, and the red here is ionized. So now we have certain conclusions about how, as a function of stellar age, we see certain patterns, but we also want to see if these patterns emerge, or different patterns emerge, as a function of galactocentric radius. So as a function of radius, we see that all the elements in neutral gas decreases from the center, which makes sense for an inside-out growth in the galaxy, which is typical for a grand design spiral. And so decreases from going in the center, but it's constant in the ionized medium. So it probably hasn't been long enough for the ionized medium to change much. And interestingly, the high neutral gas abundances for all elements, in the galactic center, you can see that the elemental abundances are quite high. Now, this has also been found in literature where Hernandez et al. And others show that indeed the hydrogen within the galaxy center is quite low in column. And so where's the hydrogen? Is it possibly in warm H2? That's why it's missed in the neutral gas. And that's what they confirm in the other paper in 23, that hydrogen actually, there's a strong emission from warm hydrogen that they detected using JWST observations. So yes, there are some warm H2 that is being missed, and hence, because we are not calculating the total column density of hydrogen, just the neutral, hence we are seeing those abundances. And one important question is whether neutral gas elements are instead tracing some warm S2 on top of the neutral gas. Sorry. So yeah. So then we separate the center of the galaxy, which is the first 14 arc seconds, with the rest of the galaxy to see if there's any certain trend showing. So the outskirts show a shallow decline in oxygen abundances, and the abundances are high in the neutral gas, which we already observed previously, but also the time scale of oxygen throughout. So basically, there's a shallow decline in the outskirts of the galaxy for oxygen abundance, which we can rely upon. Other things which we measure is that nitrogen, it seems, within its uncertainties, nitrogen, it seems, is well mixed between the phases as a function of radius. The other thing is we compared the nitrogen enrichment as a function of stellar age. So as a function of stellar age, we can see the nitrogen N over O, and here we do of different phases. Sorry, the red is ionized and the blue is neutral. And here what we do is we take a difference out of them to see if there's any trend. And we see that the nitrogen enrichment is more prominent around young stars, but although most clusters are too young. So basically, if you see, most of the points here are less than 10 million years old. So to study time evolution with this data set we need more data on the right part of the plots, both those plots. So what we can conclude from my study is multi-phase gas in small spatial scales reveal, like, first of all, rich view of chemical evolution in galaxies. And M83 is significantly metal rich, as we can see both in ionized and neutral medium, as well as different direct and strong line calibrators that we see. And as is evident, this is also evident with the excess iron enrichment in neutral gas. So the iron enrichment basically shows that it had a previous star formation history, which goes back to at least 1 giga-year. And now the new clusters, which are a few million years old, are not catching up to it. That's why the ionized gas is less iron abundant than the neutral. And then basically nitrogen and oxygen are well mixed. So there's no trace of rapid enrichment from massive stars. So one of the other studies confirmed that if there's a nitrogen enrichment, then basically the massive stars are, or like Wolf-Rayet, are with their influence of outflows, are quickly enriching more nitrogen into the gas than oxygen, which we don't see here. So we see that there's no trace of rapid enrichment. And shallow oxygen decline with radius points to the typical inside-out growth, which is common in star-forming galaxies, and also they also point out to advanced chemical processing within the galaxy. So now we have these interesting results, but what we want to do further is we want to look at, so we've already looked at M83, which is a grand design supersolar metallicity spiral. There's previous work done for blue compact dwarf, which is half solar metallicity. What we want to do is we want to extend this co-spatial comparison work between neutral and ionized gas for a chemically inhomogeneous, extremely metal poor galaxy, which is DDO68. And for that, we put in a Hubble proposal. Hopefully we get time and to observe 4 H2 regions within this DDO68, and one is already observed. And we also we also put in proposal for optical data with Keck, which we got time, so yay. And we're waiting on the Hubble proposal. So in overall, if we get the time, we can make a similar comparison, co-spatial comparison between neutral and ionized medium in an extremely metal poor galaxy. And here, I'll just end the talk with showing that we have a plethora of data from different telescopes. These are optical, Keck is accepted, so we can observe. We have LBT, we have MMT, and we have COS G160M that also has certain emission as well as absorption lines. And one of the clusters within DDO68 also had G130M. So we can see how clear the absorption lines are here, and we can do robust elemental abundances, basically. So with that, I thank you. And
any questions?
Gosh, great work. Thank you. So, I mean, there was so much information, and it's really exciting. So I need to stew on it a little bit longer. But I am like puzzled by the iron excess in the neutral gas. That I wouldn't have expected that unless. Right. So, because as you described, you have the star clusters, and you have the ionized gas, which is close to those clusters, and then the neutral gas, which is much farther away. And so enrichment takes a while. But what I would have expected if the new abundances from iron, for example, have not fully mixed in, that takes longer. So I would have expected a lower iron abundance in the neutral gas and an enrichment in the ionized gas. But you're seeing the opposite.
Yeah.
And so the only way I can explain that in my head is if the ionized gas has been diluted with primordial gas, with lower metallicity gas, and that dilution hasn't happened on the neutral gas, but it's still.
That's a great question, actually, and I even it was even in my mind that what's happening here. But we also see this in classic galaxies, and we also, the idea is that so these are young star clusters, and their injection, basically there hasn't been enough type 1a supernova to inject and enrich the gas. However, with the environment outside, with other type of supernova, the ISM gets enriched, the neutral hydrogen. However, that either due to, I don't know, shielding or some other mechanism, there's something happening that enrichment within the neutral gas isn't really getting into the ionized.
Something is enriching the colder gas.
Yeah, which is not our young star cluster.
Ionized gas that's close to the stars.
Yeah. So because these star clusters are like less than 10 million years old.
They haven't produced iron yet.
Yeah, they're not responsible.
At minimum, I would have expected a flat, that the ionized gas had the same iron as the neutral gas, but you're seeing the inverse.
The inverse, yeah.
Interesting, yeah.
Okay, Alberto, I saw your hand go.
Yeah. Okay, we'll ask something else because I think you answered the question already. When you show the plot of sulfur column density and nitrogen column density, it's very well, was there? Now it's 21. There is a hydrogen deficit compared to sulfur.
Yeah. Compared to sulfur.
And why? Why is that?
Okay, so that's what actually maybe I went in too fast. I'm sorry about that, but at least the proposed idea is that there's a warm H2 within the galactic center that we don't account when we are. So basically, the total abundance is truly would be log of NH1 plus log of NH2, or with the proper multiplication. But we don't have H2 column density because that's much further in the blue. We don't have spectra there, so we don't really get Lyman-Werner bands of it. One thing would be to actually, that's what we were discussing, that to get these abundance from here MSC to ETs back to column density and try to correct for that. But because we just have hydrogen, like neutral hydrogen column densities, so it looks like this number is quite much.
One more question.
I'm curious, have you looked at neon-based metallicity indicators?
No. I bet we have neon. I don't think we have neon lights within our, at least for both phases. Yeah, it would be in one of those phases, but that's why I think we can't. Sorry.
All right, that concludes the first session of HotSci. Please attend STS and give both our speakers another round of applause.